are the solution to homework 20, problem 2. This is a long problem. There's a lot to this. I think I probably made some mistakes along the way. I don't know for sure, but hopefully I'll be able to catch them, or somebody will be able to catch them. So we have a single piston engine, and the parameters here, the connecting rod, that's this piece right here, is 0.6 kilograms, and it's got a radius of gyration of 25 millimeters. And the crank pin to the center of gravity, this guy here, the crank pin, this guy, the crank pin to the center of gravity, LGB, is 35 millimeters, and then from the wrist pin to the center of gravity right here is 40 millimeters, right? So this is a total of, did I do that wrong? Yeah, is it 35? Yes, 35 and 50. Sure, yeah, 35 and 50, all right. So the length for the wrist pin, that's this guy, A, to the center of gravity is 50, so there's a total of 85, good. And the crankshaft length, this length right there, LOB, is 40 millimeters. The mass of the piston and the mass of the wrist pin and the piston together are 0.8 kilograms. And the engine's running at 3,600 RPMs, which is pretty fast. And we're going to ignore the mass of the crankshaft and ignore the forces due to the gases in the cylinder, which would be the thing that would be driving this piston. Okay, so it's really just maybe an empty cylinder at this point right here. No vacuum, no pressure, nothing going on here. But we're going to find the magnitude of the forces on the wrist pin, right, at A, and the torque that's on the shaft. All right, so I happen to actually have a little piston right here. All right, so this is an engine that I mess around with, and if you want to, this is the wrist pin that we're talking about here. So you want to get know your nomenclature right here. So this is the connecting rod and the wrist pin, like your wrist that way right there. Just goes back and forth and put it through there. So we have this coming on, and here's the crankshaft right here. Here's a little crankshaft, and of course the piston rides on the crankshaft here, rides right here in this crank pin. I think that's the right name for it. I think so. So anyway, put this on here and goes flippity-flop around, and we make power. So here you go. And I usually bring these into class, and this little thing right here dips into the oil reservoir and throws oil all over the place. So that's this way of spreading oil and getting lubricated. But anyway, and so the crankshaft length is from the center of this to right here. So that's that length right there. So now you have a little bit more of an appreciation of what the physical thing that we're actually looking at, we're actually talking about here. So I tried to use real numbers because this engine that I have from this half horsepower engine from Harbor Freight that I bought for $92 a couple years ago is all these parameters are pretty close to being what is in that little engine. So one of the first things that I'm going to do here is find the moment of inertia of my connecting rod. That is not a vector, that's just a hat for it. And we were given the radius of gyration, so we used KAB squared times MAB, and we end up with 0.025 squared, and the mass is 0.6. So we get a very small number of 3.75 E minus 4. And these are kilogram meters squared. I decided to keep it into SI units for here. A little bit of geometry at this moment right here. I'm going to call the angle that we have right in here, I'm going to call it beta. So beta is equal to, and we know this length, so let's call the length LA, AB is equal to LAG plus LGB, or 50 plus 35, 85 millimeters. So we're going to take the inverse cosine of the distance here, LOB. So that's going to be my LOB. I went 0.4, what did I do right up there? 40 millimeters here. 40 divided by 85, and I believe I get 61.93 degrees. And maybe I want to write this other angle right in there. I tend to need this one. I'm going to call him phi. And phi is just going to be 90 minus beta, which ends up being 28.07 degrees. That's often useful to me. All right. So we know something about this already, is motion. So let's do the kinematics. Find the acceleration at B. So I'll write out as a diagram there. It's a good place to start. All right, that's the diagram. All right, so we get the omega OB is rotating that way. So the velocity of B is that direction. And the acceleration, okay, and this is a constant, and we should have said that constant. I think in the problem statement I better have said it was constant. We're going to get the acceleration of B with respect to O in the normal direction, which is entirely the acceleration of B, is going to be omega OB squared times the length of OB, which ends up being, oh, and we need to convert, right? So the conversion of this, we divide by 60 to get into revolutions per second, and we multiply by 2 pi to get into radians. So this is 2 pi radians per revolution. And we're left with a value of 377.0 radians per second. So down here we have 377 squared times the length of 40 millimeters, or 0.04. And I think it'll be 5,685 meters per second squared, which is that's pretty fast. It's kind of surprisingly fast, but that's what that does. We also should do a velocity analysis, and as we go to so as we have this velocity, and we might want to find the velocity of A. But if we go to do a velocity analysis here, we see that we have velocity of B coming down, right? Velocity of B. But we know the velocity of A has to be along here. So if we try to do a ICR of this, we would see that these are parallel lines, right? So our conclusion is that omega AB is equal to 0. Like I might write ICR is infinity, therefore there. I might use this space over here, right? So I could have, if I needed to. So this has no angular velocity. That's going to simplify the problem a little bit. But now we do the acceleration analysis. Of AB right here, and take this right, and we know the acceleration here of B. acceleration of B. We already have that value right up here. And we know A has to be either up or down. Right? It can't be it can't have any left or right. So we do the same thing we've been doing before here in our kinematic analysis. We will apply all of these over to there, right? I could also, at the same time, I want to know something about G right here, my acceleration of G. So I'm going to draw, I'm going to use this same diagram, just be aware. All right, so I know, I want to find the acceleration of A, and I know the acceleration of B, so I used the acceleration of B as like the translation of this. So I'm going to have a tangential acceleration here. And there is no normal acceleration, right? And we could even draw it in there just as a placeholder. And acceleration of, this is A with respect to B in the normal direction is 0, because that is 0. Right? This would be the omega squared times the length of the thing term if there was an omega. There's omega 0. Something I know is that this is the acceleration of B, so it can't go horizontally, so this one must have a positive x direction. So this is the way that I know my acceleration of A with respect to B tangentially should go. And therefore, my alpha, call it AB, should go in that direction. And then lastly, this angle is going to be that same as that phi, right? It's the same as the angle right there, which we found to be like 28 degrees. So I can find from this, right? So I could say the acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B tangentially plus acceleration of A with respect to B in the normal direction, which we know is 0. In the x direction, we end up having 0 is equal to negative AB, which is 5,685, plus, we're going to have this component right there. So it's going to be alpha, which you don't know, AB, times the length, 0.085, times the cosine of 28.07. From that, we can find alpha AB. And I want to double check my values, but I got 75,800. So we go 5685 divided by 0.085, all right, divided by 28.0, cosine of 28.07, 75,800 radians per second squared. And now in the y direction, we're going to have the acceleration of A, all of it. There's nothing in, no acceleration of B. And then this one is entirely going to be upwards. It's going to be alpha, which we just found, 75,800 times the length, 0.085, times the sine, because it's that guy right there, sine of 28.07. And what I find is my acceleration of A is 3,032 meters per second squared, which is pretty substantial. 3 here. Problem 2 continued. And I kind of want to use my same diagram here because I'm feeling lazy. I could. Maybe I'll redraw the thing out right there. It's not that hard to do. This problem is supposed to demonstrate how kinematics and kinetics in rigid bodies are associated. Right? So we had this acceleration of b, and we were like doing almost a full kinematics problem to start with. Sorry. So here's the acceleration of a. We just found that. We want to have the acceleration here, and I don't necessarily know whether it's up or down, or left or right here. I kind of know which. I know that it's going to be to the left, but I'm pretending. Acceleration of g in the y, acceleration of g in the x. Well, this is we already know this one, so I'm just going to leave it with this, right? We could use this because we know it, but I'm going to stick with this one. So we're going to stick it right here and stick it right there. So here's the acceleration of b and the acceleration of b, because in the x direction. So we're going to pin it where we're using as the reference right there. And now we know that the alpha is this way, and this is the acceleration of g with respect to b, tangential direction. And that right there remains phi. So we write out in our equation the acceleration of g is equal to the acceleration of b plus the acceleration of g with respect to b, tangential, plus the acceleration of g with respect to b in the normal direction. And we happen to know that's 0 because we didn't rotate. So in the x direction, we get AGX, because that's what's written up here, is going to be equal to a negative 5,685, right? Because we get that from here. The acceleration of b, plus alpha, which we found to be 75,800, times this length right here, which is 35 millimeters, 0.035, but it's only the horizontal part, so it's the cosine of 28.07. We get the acceleration of g in the x direction is going to be a negative 3,344 meters per second squared. So it's actually that direction right there, which is probably something we kind of knew. In the y direction, we got nothing right there, 0. And here we have plus. We're going to have this, but the sine of it, right? So the alpha is 75,800 times the length, this length right there, 35 millimeters, and then the sine of 28.07. So the acceleration of g in the y direction is 1,235 meters per second squared. Right, so we did all this. That's all the kinematic portion of the thing. That was a lot of kinematics, wasn't it? Now we go on into the kinetics of the rigid body. So first off, let's do the piston, because that has mass and we know its acceleration. What is its acceleration? Is going to be the same as a right there, right? So we do an FBD and an IBD, and here's my x and y. of the piston. And try to make them look a little bit like each other. I don't know. I got it kind of close. And they're equal. And we can put gravity in there. I went ahead and put gravity. So I go MPG. But we have this force that's acting, this pin that's onto the thing. So I'm going to break it into X and Y, and this is going to be FAY, and here, arbitrarily, by the way, FAX, right? This is the pin, this guy, that's the pin forces acting, right, onto the piston. Or maybe I should say the other way around. It's this right here acting on this, right? And these terms of one thing acting on the other are really important in your free body diagram, that you get them straight, right? That which one, who is acting on to whom, and then when we go to the next part, they have to be equal and opposite. So the acceleration, I'm going to guess, is, well, I know the acceleration, right? So it's going to be the mass of the piston times the acceleration of A. So summation of forces in the y direction equals mass times acceleration in the y direction. So we have FAY minus my mass of my piston, which I said was 0.8 times 9.81. It's going to be equal to, over on this side, 0.8 times 3,032. So FAY, if I did the math correctly, was 2,433 newtons. So for my next part of this thing, I want to do the FBD and the IBD of the connecting rod. Oops. Messed that up a little bit. And so, okay, so I know this force right there. And that's going to be FAY. And you'll notice it's equal and opposite right here. This one I don't know the direction of, so I'm going to keep him as positive. And so this is the FAX. I know I drew it up there, but that was just kind of a placeholder because there needed to be something onto it. But now we have, I think in my original problem here, I went ahead and I put the weight, right? So we get the MAB times G of the center. And then we're going to have the force of B in the Y. And then, right here, FBX. So here at the center of mass, I know the directions, right? So I don't have to pretend. Yeah, okay, so I was able to find up here that I was going upwards, and here I'm going left, right? So I'll draw those on there. So you get MAB, AGY, MAB, AGX. But we also have I of AB. We call it, yeah, we use the bar alpha AB. We don't know this AX and we don't know these, so I think the best place to take the sum of the moments is about B to start off. Then we can find this. But we need to do the sum of the effective moments because this is rotating and translating at the the same time. I guess I decided that counterclockwise was positive. So this is a lot of writing. It's going to take a lot of space right here. Let's see if I can do that without cluttering it up too much. Here's a negative f ax, and it's going to be times, remember that this right here was beta, and I'm not going to use symbols, I'm just going to use values here, but the beta was like 61.93 degrees, right? So that's, we're going to use that 61.93 degrees for beta right here, and the length of this is 0.85, so it's 0.085 because 85 millimeters. So it's only this distance, so we end up with the sine of 61.93. Right. This one we know that force, and that's counterclockwise, so we're going to stick that downwards, and 2,433, right? And it's also 0.085, but its distance is now going to be the cosine. So we get the cosine of 61.93. And also we have the mass of this thing of 0.6, and this distance is 35 millimeters, or 0.035, and is also the cosine of 61.93. All right, so those are all the four moments that are acting onto this side. Now we need to do this. Now we need to do the effective moments. So you had to be careful here. I'm going to start out with this guy right here. So we have our I, which we found to be a very small number, 3.75 e to the minus 4, times our alpha, and our alpha, we found it to be 75,800. And this is a negative number, right? Because it's going clockwise. Let's see, this is the next one that I did. I decided to go with this guy, which is actually counterclockwise. And so I take the mass of this 0.6. I don't know if I have enough room. No, I don't have enough room. But I'll just do my best. 0.6 times AGX, which we just found up above, was 3,344. Now we have to do the length of this, which is 0.035, but remember, we have that angle right there, so it's this, but we have to only go this. So I think that's going to be the sine. Did I do that one? No, I got it right. Sine of 61.93. Makes more sense. 61.93. And then lastly, this. And that's going clockwise about here, right? About this point, it's going, okay. So minus 0.6, and its acceleration was 1,235. And its moment arm is 0.035, and it's only the cosine of 61.93. Boom. What we end up finding is that the force in the x direction is going to be 1,014 newtons. That's not very exciting. But we can also find now from the same free body diagram the sum of the forces in the, which one do we want to do first? I guess go the x direction equals mass times acceleration in the x direction. I don't actually need to do this one, but I did it anyway. So I have FAX is going positive. Oh, just write that on the value. 1014. And then I'm drawing this one F plus FBX. All right. And then nothing else is in the X direction over here. Right. So, but over here, this is in the negative direction. So I got negative, and I got a 0.6. And then times my acceleration in the X direction, 3,344. And I find FBX was equal to, I said, negative 3,020 newtons, right? So it's actually pointed the other direction right there, boom. So, but remember, that's going to be this part acting onto that part, right? That's the force that the conrod is feeling from the pin. So So the pin actually feels the conrod pushing back onto it. And then the last one, summation of forces in the y, mass times acceleration in the y, upwards. And so we have FAY coming down, which we know to be 2,433 from the piston. We got gravity working against me, 0.6, 9.81, and then plus FBY is going to be equal to the mass of this, and that going upwards, 0.6 times the acceleration of the center of gravity, which was the 1, 2, 3, 5. And so we find the force in the y direction is going to be 3,180 newtons. All right, so now we're getting near the end. All right, so we're up to page 4 into this, and this is problem 2, continued, ... So let's see. We have, we needed the torque onto the piece. So because this is massless on the connecting rod, right there, all we need to do is an FBD. We don't need to worry about the IBD because it's not, let's say, going that way, right? It's not. Whereas it might be accelerating, it doesn't have a moment of inertia or mass, so it doesn't have an inertia, so it doesn't need an IBD. So the force that we just found in the y direction here, it's upwards, is actually downwards right there. This is our FBY. There's going to be a reaction right here at the FOY, but there's also a torque that's being applied onto there. And that's going clockwise, so this must be going counterclockwise, and that's going to be the torque of the shaft onto this. But then this thing is actually putting a torque onto the shaft in the other direction, right? Okay, and so we take the sum of the moments about O is 0. That's because crank is massless, or we're neglecting the mass of the crank. And so we see that torque minus our FBY, which is 3,180 newtons, times the crank length, which we said was 40 millimeters. So the torque is equal to 127.2 Newton meters. It's interesting though. This seems like a completely this is instantaneous power, so it shouldn't be considered that's what the power of this thing is, right? And for the most part, this doesn't. This is just inertia based things, right? So it's like an instantaneous thing. So it's there's nothing driving it, right? There's no pressure inside the cylinder, so it's not actually produced power. So I could actually take this torque and multiply it by the RPM, but it makes absolutely no sense. So I'm not going to go down that rabbit hole right now. But it is something I thought, that might be a neat thing to do. But let's just write out what the answers are. And we had to be careful because of the phrasing of this problem. And I asked for the magnitude, didn't I? Yeah. Because I asked for the magnitude, I guess I don't. I wrote the magnitude on, but if it's just the magnitude, then I don't have to give the direction, so it doesn't really matter. So somewhere in here, I'll write down the FA is equal to the square root of these forces that are acting on here, 1014 squared in the x direction, and the other one I got from 2,433 squared. So yeah, that's the way I asked the problem, so I'm gonna stick with it. 2433 squared plus square root, and we end up with 2,636 newtons. So FA magnitude 2,640 newtons, and B, the torque on O as a vector. This torque is O acting onto the shaft, so ours is the other direction. So 127 Newton meters going that way. And here's going to be my answers. Be interesting to find out if what I got wrong, if I got something wrong somewhere along the way. But I think this is the end of Newton's second law for rigid bodies and all that you've covered in this semester for Newton's second law, which seems to me, I'm not 100% satisfied that that's enough, but I don't know where else we would get the time. I suggest that you do some more Newton's second law problems as in rigid body and in particles. It's one of the most important parts of our semester, so I really encourage you to do some more practice problems before the exam. Long problem.